Alright, hey guys, what's going on? So today we are going to be talking about the Weyl Tensor. The Weyl Tensor is something you typically learn in more advanced GR, but it's going to help us get to somewhere really interesting. This is a stepping stone to something we're going to get towards, which is the Ruse-Lanczos identity, which is a super interesting identity, and it will help us understand complex tensors pretty well, right? So with that being said, make sure to hit the like and subscribe button. Become a member if you want to become a member, where you'll get member-only videos, and go into my Patreon page if you want to support the channel and get notes as well. Again, if you're interested in Patreon, if you want to know what the difference is between Patreon and becoming a member here will enable you to get member-only content, okay? Becoming a member, contributing on Patreon right now will just get you access to the notes, okay? At some point, I'm gonna aim to put both in one place, and where the notes will be a little bit less expensive than gaining access to the member-only content, okay? So let's get straight into the material now. Okay, so the conformal so we're talking about the Weyl tensor today. The Weyl tensor is important because it tells us something about conformally transformed curvature. Okay, so let's step back a little bit. Let's talk about this manifold. We've talked about the structure before. This complex transformation, a conformal transformation of the tangent space, means that the inner products are preserved. Okay, so we talked about this before. We talked about what exactly a conformal transformation was. So in this metric space, this means that the metric tensor is preserved under conformal transformations, right? So we have this metric, or this inner product, that tells us we have a metric space, okay? That metric space is lives within its own space, and that thing is preserved under these conformal transformations. So we now aim to understand conformality. And so before we do that, let's recall a few things. So recall the Riemann Curvature Tensor and the transformed Ricci scalar. Right, so the transformed Riemann Curvature Tensor was this guy here, where we defined what these B tensors were. The conformally transformed Ricci tensor, okay, is this guy. And the conformally transformed Ricci scalar is this guy. So this is stuff we've seen before now in our last video, titled Why GR is So Freaking Ugly. That's not what it was titled, but these really tested our patience, if you will. There was a lot of math that went into that video. My intent wasn't to scare you guys off, but to show how hard this can be. But in showing how hard it can be, I hoped to have showed you how satisfying how satisfying it is to come to an answer that is relatively not as ugly as all the intermediate steps. And that's the beautiful thing about this kind of stuff, is that things typically get ugly before they get really nice. And so that's kind of the story that's going to happen here. It's not going to be as bad when we're talking about the Weyl tensor now. So let's just continue with this. We can use the conformality, or the conformally transformed Ricci scalar to calculate this here. So we're multiplying the conformally transformed metric with the conformally transformed Ricci scalar. When we do that, we get this. All right, and then we get this here. Okay, so we just multiply everything out. Remember, this times this is just going to give us 1. So we get something that looks like this. And then we can take this to this equation, this side of the equation, this to the side of the equation, divide everything by 2 times m minus 1, where m is, again, the dimensionality of the manifold. And we get this right here. We can then plug this into the conformally transformed Ricci tensor. So the conformally transformed Ricci tensor is this guy. So now that we have, we're taking this, we're subtracting this guy here, right? So we take this to this side, and we have, let's see, this guy here, which is this guy here, which is this guy right here, minus this here, and we get this in here, okay? So we're just rearranging a few things, and when we rearrange those things, we get this equation here. So this is another equation for the B tensors, right, in terms of conformal transformed Ricci and Ricci tensors and Ricci scalars. Where this is the Ricci scalar part, and this is the Ricci tensor part. So these are, we want to put 2 pins in these guys, right? So let's box them up, because we're going to use them later. This guy and this guy. We now calculate the conformally transformed contracted Riemann curvature tensor. So that's this guy right here. So we're lowering rho to get kappa. Okay, so we get this guy, and so we get all of this, right? So we get from here, okay, to here. So here are all those beta tensors, or B tensors, and we're multiplying all of this by the conformally transformed metric, which is right here. All right, and then we multiply everything through, and when we do that, we multiply this metric in with these, and things will contract, things will lower, and we get this guy right here. All right, so let's put a box on this guy here, because now we have a conformally transformed, we now have equations for this, this, and this. Okay, plugging in the B tensor now into this equation, we get all of this. Okay, so more color coding, right? Because things get a little bit complex. So we have this guy here, so this guy here, and then we're taking this here and we're plugging it into each one, and we're labeling the indices rightfully. Hopefully, if you catch a mistake, please let me know in the comment section. And so we get all of this, and then what I'm doing here, again, you can pause the video if you want. I'm tracking everything. So we get, let's see here, this can all be rearranged, right? Because we get this times this, and we have, actually, so, okay, so we're multiplying both sides by this, right? So we get this, this, and then here is this guy, right? Here is this guy, okay? And here, this guy is right here. So all these conformally transformed metrics are down here. Everything I've circled here, I've circled here, and all of these guys are going to be kappa nu, kappa sigma, mu sigma, mu nu. Okay. So hopefully the color coding helps to understand how we get from here to here. Okay. All right. And we're multiplying everything by these metrics, and that's why we get all of. So we have this mu sigma, mu sigma, mu sigma, mu sigma, mu nu, mu nu, and mu nu, and so forth. Okay. Alright, so we can bring the barred terms to one side of the equation. So the barred terms, I mean the transformed terms, right? So the transformed terms are these terms, okay? And when we do that, we get to this point here. So everything, I realize my face might be obstructing some of this. So all these barred terms, right? And then on the other side of the equation, we have nothing that's transformed. So this and all of this here. So recalling the scaling of the metric is this guy. We can replace a lot of things now. And so we have now, I don't think I changed anything. So recalling the scaling of the metric. Okay, I see. So now I'm bracketing this up here, and I'm taking this out. Okay. Okay. So we have this times all of this is equal to all of this. So without this here, we can realize that these two guys, these look very similar to each other. One's just transformed. All of this looks very similar to this, and all of this looks very similar to this. So what's this saying? This is saying that this thing is conformally, everything in here is conformally transformed, but everything in here is not. But both of these two look the same. So what we can do is we can define this whole thing as a tensor, and this is just the conformally transformed tensor. So we have this times this is equal to the same thing again, just not nothing's barred, nothing's transformed. So without this factor, we can see both sides of the equation are equal, so we can define this new tensor called the Weyl tensor. So this is the Weyl tensor, the C tensor, and it equals all of this in here. Okay? So therefore the Weyl tensor is defined in this way. Okay? And taking antisymmetry of this tensor into account, we can write this guy. So this just compactifies a lot of this. We're going to see some very interesting geometrical interpretations of this as well later on. Okay? So we can contract the Weyl tensor with the metric tensor. Let's do that here. So here's our metric we're contracting with, and the metric we're contracting with we can say is conformally transformed because of this guy. Right, so this is equal to this. And so we can see that when we do that, we get kappa upstairs. And actually we should get rho upstairs, right? This should be a rho. Right, so it should be rho. And and then this should also be rho as well. The point here is that this thing is the same. So what happened here? So rho mu sigma nu, we have rho mu sigma nu. Okay, nothing changed on that side. So this shows that the conformally transformed Weyl tensor is no different than the untransformed Weyl tensor, or the conformally untransformed Weyl tensor. And so this means that the Weyl tensor is invariant under conformal transformations. Okay? So what does this mean? Let's again recall what exactly is a conformal transformation. A conformal transformation takes us from something that is curved to something that's conformally flat while in the process of maintaining angles. Okay? So all these angles here are maintained, but a conformal transformation takes us from a space that's curved to a space that's flat, okay? And the metric here at some point is going to be transformed. This is a conformal transformation in this way. And what we found is that all of these are all the equations that tell us what happens to the Riemann, the Ricci, and the Ricci scalar. What happens to them during this conformal transformation. Okay? So what happens to the metric is this. What happens to these guys as a consequence of this is all of this. Okay? But then we have this interesting object called the Weyl tensor that actually doesn't change at all during this transformation. Okay? This is quite interesting, and it's going to turn out that this Weyl tensor gives us some interesting properties about the curvature of spacetime, and we're going to get into that now. So we can calculate the trace of the Weyl tensor. When we do that, we're summing kappa over kappa, okay, and we just identify all the kappas, all the rightful kappas in here. And then when we do this contraction, we contract everything, right? So kappa sums with kappa, we get mu nu, and we can do the same thing here, right? So our kappa kappa is going to be the Ricci scalar. All right, we get this next, right? So we're just rearranging a few things, right? Because this here is going to give us this m term. All right. So again, the m is the dimensionality of the manifold that we're dealing with, and so we get this. So therefore, the Weyl tensor is traceless, right? Because we got this here, which is this, and this minus this is 0, right? So these two guys cancel out. These two guys cancel out because they're all the same. And so what this is telling us is that the Weyl tensor is traceless. Okay, so this is quite interesting. The conformally invariant part of the Riemann curvature tensor is the traceless part of the Riemann curvature tensor. In spacetime, we're given three objects, right? That tell us something about spacetime. The Riemann curvature tensor, the Ricci tensor, and the Ricci scalar. The Ricci tensor told us something about volumes. The Ricci scalar told us something about areas. So in one case we have volume-induced curvature. The other case we have area-induced curvature. So what the heck is the Weyl tensor? The best way to sort of deduce what the Weyl tensor might do for us, you can look this up anywhere, is that, okay, we have volume, we have area. What about shape? Could the shape of an object induce the curvature or change the curvature in some way as well? So that's exactly what it is. It's so on one hand we have volume-induced curvature within the Riemann curvature tensor. We have area-induced curvature within the Riemann curvature tensor because we have the Ricci tensor, or the Ricci scalar here. We have Ricci tensors in here, but then we have this guy here. Right? Because we defined this as the Weyl tensor, we just rearrange these two guys and we get this here. So on one hand we have the curvature that's induced by volume, right? So all these pictures that we went over when we talked about the Ricci tensor. And then this picture here we went over when we talked about the Ricci scalar. Okay. What's left for us is how shapes move. Okay. Volume's not necessarily changing and areas are not necessarily changing, but the shape of things is affecting curvature as well. Okay. And so this is the insight that we're going to attribute to the Weyl tensor. I wouldn't put too much stock in this idea that it's shape-inducing, but it is when you look it up on Wikipedia, when you look it up anywhere, most places will say that the volume curvature is typically associated with the Ricci tensor, whereas the shape of an object tells us something about the tensor, or the curvature as well, and that's given to us by the Weyl tensor. Okay, so that's what we want to go over today. We notice also really quickly that the Weyl tensor, actually let's go here, we can actually define a case now and say the dimensionality of our manifold is 2. The dimensionality is 2, we get a problem. Right? So I'll automatically see we have a problem here. Because this would be 0, can't divide something by 0. So something interesting happens when our dimensionality is 2 to the curvature. Alright, similarly, if our dimensionality is 2, we get problems here as well. Okay. However, anything above 2 is fair game. So 3-dimensional. Right, so in 3 dimensions, this we actually get 3 minus 2 is 1, 3 minus 1 is 2. This is all fair game. This is all fair game. And we get, we can actually get a formula for our Weyl tensor. So this is interesting, right? So at our dimensionality of 2, there seems to be some interesting shift that happens in curvature. Okay, we go from undefined traceless curvature to defined traceless curvature when we transition between dimensions. So let's keep that in mind, because this is going to be something that plays a role when we start talking about conformal field theories a little bit more, okay? So with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.